set that in motion. Cool. Welcome, my vast crowd. Today, as part of our little coding and biology series that we're doing in a collaboration with a few of the other iGEM teams, we're going to talk a bit about a programming language called Julia. I'll try and make that a little bit bigger for you, so it's not quite so small. And then after we talk a bit about Julia as a language in general, we'll move into doing some data processing with it, and I'll walk through an example that I worked on earlier for our team. We did some growth curve analysis, so it should be a cool little demonstration of what makes Julia unique, how it compares to some other programming languages, and then we'll flow into kind of a longer example of how you might write a Julia program and what sort of things it can do. So we'll start with the obvious question, which is, what is Julia? It's a modern open source, high-level programming language designed for scientific computing. So that's a lot of buzzwords there in the same sentence. But the idea is it's meant to be a nice programming language to use, which is part of that high level. That means it's kind of close to how humans would intuitively think about problems, as opposed to being close to the machine, which is more low-level programming. So Python's a good example of one that's high level. It reads almost like English. But despite it being, designed for specifically scientific computing, it also is a bit of it remains a general purpose language. So it's not something like MATLAB or R, where it's quite focused on solving one particular problem. R being a statistical programming language, and MATLAB being, optimized for a set of engineering tasks. It's a bit closer to Python in that way, that you can write all sorts of types of software in Julia, but it still does have those tools that make R and MATLAB nice to use when it does come to scientific computing. So that's great, but why would you use Julia in particular, especially if I've just said that it's quite similar to Python? Well, despite high-level languages like Python being quite popular in scientific computing, this is usually for their ease of use. So if you've seen some of the earlier workshops put on in this series where Python was discussed, you'll probably know Python's a quite nice language to use, similar to English, easy for scientists to pick up and start using quickly, even if you're not a fully trained computer programmer. The downside to this is some of that comes at a cost. Python programs, if you've ever tried to run a larger Python program, they can really slow down a bit. An example is, over the last summer, I've worked on a project with my soon-to-be PhD supervisor, in which we're doing some analysis of mass spectrometry data. And the original prototype for this was written by his last PhD student in Python. And so it has to do things like look at these molecules that make up the cell wall, which are kind of this branching structure, and split up those branch structures into all the possible fragments. And then it goes and it looks through the mass spec thing to try and find all those fragments. But the point is, this fragmentation takes a long time, or it's a really complex operation. If you're fragmenting a small molecule, that's okay, but as the size of the molecule increases, the amount of time it takes to fragment it kind of like exponentially goes up. The problem with that then, being written in Python, is it started to take like 15 to 20 minutes to get results. So I'd write some code, and of course I'm prototyping now, working, trying to figure out how to solve the problem a bit interactively. And I'd write some code and then I'd go to test it. But if I wanted to figure out if my changes were correct or if I had messed something up, it could take me up to like 20 minutes to generate the full set of output data again. And it was very difficult to speed this up in any way, because Python's hard to run on like several cores of a computer. Julia is very much optimized for this type of high-performance computing. They've run it on some supercomputers with, relative ease. But what typically happens with, say, a Python program that you prototype this way, and what's happening now, is that program that the last PhD student wrote, he's now gone off to a software company to help them write this whole program again, a second time, in C++, which is a different programming language that's designed to be quite, or a lot more high performance. The downside, of course, in that is being that C and C++ are much more difficult languages to pick up and to make changes in than Python. So you could end up in a kind of bad situation where, okay, maybe they want to add a new feature, so they struggle to add it to the C and C++ version because it takes a long time to write that code, so maybe they go back to the Python one, but then to make that feature fast again, now they have to write it back in C and C++. So there's lots of this back and forth between two different programming languages, often in scientific computing, because you want an ease of use that scientists can use it, but you also want the programs to be fast enough that they're actually useful in the long term. But Julia has come along to try and solve this problem. Julia is meant to not only be that nice high-level language, but to also be incredibly fast when it's run on a computer, so you can get through large data sets quickly. Just how fast? Well, here's a cute little graph. It's probably a bit small, so I might try and make it a bit bigger, if I can be so brave. There we are. So, here's a set of different benchmarks, each little colored dot being a different computer program or problem that's being solved. And then across the x-axis here you see different programming languages, and you have how long they take compared to C, which is kind of like this, like I mentioned earlier, it's a low-level language and it's kind of the gold standard of computer performance. The code is a bit tricky to write, but it's meant to be about as fast as you can get it, because you can apply all those clever optimizations. But the real takeaway from this graph is that these higher-level languages over here, Octave is like a clone of MATLAB, but an open source version. You can see that one's the slowest, and this is actually a logarithmic scale here. So everything at this line here, this 10 to the 1, means these programs take 10 times longer to run than the equivalent program in C. Once you get up here, God forbid, that's, I guess, what, 10,000 times slower than the program in C. And the trend you can see here, which may be a bit challenging if you're working with these languages for big scientific problems like Python and R, and even down to MATLAB. Oop, we have a new person wanting to join, so we'll let them in. There we are. The challenge with some of these higher level languages is they perform quite poorly when compared to C. So here you can see Python, where some programs aren't too bad, like this matrix multiplication one. Another person, lovely. Programs aren't too bad, like this matrix multiplication one here. There are some other programs that are up to 100 times slower, like this recursive Fibonacci sequence computing program. The nice niche that Julia occupies is way over here. So Julia, despite being about as easy to program in as something like Python, is much, much closer to that level of C performance. You can see even some programs here are running faster in Julia than they would in C. And this is kind of why you might want to use Julia and why it solves that two-language problem. We have to keep rewriting code. It's because you can write it once in this nice-to-use language, and that'll give you basically all the performance you'll need for down the line. Perhaps you can see some niche cases in which you'll still want to write something in C, but for the most part, this performance is close enough not to be as much of a bother. Uh-oh. Ha! Imagine that. That's very funny. I haven't been sharing my screen. So, let's share my screen. Good catch there. Definitely not just you. Definitely fully me. So, there we are. Can you now see the beautiful little graph here? We'll hope that is a yes. Yes, excellent, fantastic. Right, so, sorry for talking about a graph that you couldn't see for ages. Here, like I was just talking about, is that graph. Just to real quickly go back through it, because you've already heard the spiel, but just to point out some things with the pointer here. Yes, this is that graph that has all the programming languages along the x-axis there, and then has the different programs as these different dots, where the y-axis is how long they take to run relative to C. Oh, exciting. Everybody's pouring in now. Cool. So yes, the takeaway from this graph is that languages that you might use for scientific computing already, like R or Python or MATLAB, are often much slower than harder to use languages like C, but Julia manages to be as easy to use as these higher level languages and optimized for scientific computing, but lots faster. As you can see down here, closer to the C program, whereas some things up here might take 100 or 1,000 times as long to run. Cool. So, in addition to just speed, of course, Julia has several other little advantages, and it compares these languages in different ways. Julia's documentation actually has several pages of information which explain the important differences between Julia and other popular languages. So here's an example of that. They're comparing it to MATLAB, which gives some quite technical comparisons if you're used to using MATLAB. Same with R, same with Python, and then same with some other languages like C and C++, or even Common Lisp, which is a bit of a niche one, but one I have a soft spot for. To summarize, though, where it kind of draws its inspiration from Julia, you can think of it being similar to MATLAB and R in that it's a programming language developed with scientific computing in mind. But unlike MATLAB, it's open source, which means anyone can use it, anyone can contribute back to it. You don't have to pay a horrendously expensive MATLAB license or be in education. And also, unlike R, it's more flexible, similar to Python, and so you can use it for general purpose programming. It kind of combines, that high-level syntax of Python with the speed and efficiency of C++, so that's that solving of that two-language problem. And it also tops it all off with some powerful features that are probably more focused towards computer scientists or people writing a lot of code, but these things called multiple dispatch and metaprogramming, which we might have a little bit of time to briefly talk about, come from Common Lisp, but they've made them look a lot nicer visually, a bit easier to understand and use. But these are features that can help you really avoid repetitive code, so it saves, again, the programmer more time. Now, with all of that being said, there's no perfect tool for every job, so where might you not want to use Julia? Responsiveness is kind of the big thing here. Julia's same trick that it uses to be a high-level language like Python, but to be really, really fast, is that when your code runs for the first time, it transforms it into some optimized machine code that your computer's better at reading. But because it's this high-level language and it's something called dynamically typed, so like the way your program runs can depend on the data you feed it, so you can't always predict exactly how it'll run, so you can't predict the machine code before running it sometimes. That means the first time you run a program, so you say you want to plot something, it's going to have to compile all that code after you enter that, line of text. And sometimes that takes like tens of seconds. So you might open your Julia, think, yes, this fast programming language, and then go to plot something, and it might take the first time you run it like 10, 30 seconds to get all those packages loaded and run. Trade-off, of course, being the second time you run all that code, it'll happen in microseconds. But it's this original large latency, which can sometimes be tricky with some interactive things. Or you can imagine it being a problem if you need like some really responsive code, like something operating some robotic equipment that needs to respond quickly to changes or stuff like that. Another problem might be that Julia is really meant to be run by other Julia users. It's a bit hard to take these Julia binaries, applications, and transport them to other people's computers without taking all of Julia with it. This is pretty similar to MATLAB, R, and Python. All those languages you need to have installed on your computer to run the code anyways, but it is different from something like C or C++, which you can write an application in and not have to install all of C and C++ to run. While it's a smaller installation than something like MATLAB, it's a bit more lightweight, it is more heavyweight than R or Python, so it is a bit of a decision sometimes to use Julia because you have to download the whole, Julia runtime. The last thing, of course, being one of the more obvious ones, it's a relatively young language. It's new, there are still some rough edges, and the ecosystem around this language is still changing quite quickly. So whereas Python, you can search how to solve blah 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 in Python into Google, and you'll get like a million answers. Julia is still kind of getting to that point. And because it's changing quickly, sometimes it's tricky to find up-to-date learning resources. They are there, and they're very high quality, but you might have to do a bit more digging than you would if you wanted to learn something like Python. But with all that being said, that's our little introduction to Julia, why you might want to use it and why not. You might want to use it because it's really quick and high level, so it can solve that two-language problem, and you might not want to use it if you're doing something that requires low latency, or maybe portability of the program, or if you're just trying to learn something that's a bit easier to learn, I guess, overall in terms of learning resources. Cool. With that being said, let's jump onto the parts of Julia, a bit of a whirlwind tour that makes it such a cool language for doing scientific computing in. The first thing I'll show off, which hopefully you'll be able to see, is this what's called a Julia REPL. Cool. So I'll just double check. Can people see? I'll move this to my other screen. That nice Julia window here. Hopefully so. The one that's popped up. Lovely. Excellent. Fantastic. So this is the Julia REPL. It's a read, evaluate, print loop, which means you write some code in here, whatever you want. Say, you know, print hello world. If you can manage to type that. That took me some effort. And you press enter, then the code is read, evaluated, which means it's actually executed to do the printing of hello world, and then printed back here, obviously, and then you loop back around. So now you can see I can put in more things here. You can do like basic maths, so you can do 2 times 2 is 4, so you can see that reads that code, runs that code, prints that code, then loops again, which is quite useful. This REPL is a bit more, though, than just like your typical terminal interface. It's more sophisticated than equivalent ones like in Python. One of the things that makes it a bit fancy is Julia has really good Unicode support, which means it supports characters that aren't like on the keyboard normally. This is good both for like foreign languages, but also for mathematics, which is a bit of a language in itself. So for example, you can of course type pi spelled out to get pi, the number mathematically. But also, you can see Julia supports using the symbol. So to input these special symbols, it's the same as if anyone's ever used LaTeX before. You can put like a \n, put the name of something, then press tab, and it will change it into the symbol. And you can see you can use that symbol the same way you can the full name. So this makes your equations look a bit nicer. Say if you want to do like 2 pi, for example. You just put in 2 pi, and then there's your answer. It looks exactly like you'd write it out in maths. Another nice thing is it's got built-in package management. If you press the, let's see, that symbol, the closing square bracket, but without those quotes. If you just press that, it switches you into package mode, and it's from here that you can do things like add like a plotting library, which would be Gadfly, which we'll use later today. So you can do that, and then it'll download this package and install it all for you. You can do this all from inside of the Julia REPL. You don't need to do something like you would in Python and do pip install and make sure you have everything installed correctly the first time. You can do that all from this interactive environment. I can also probably cancel that whole installation because I don't need to do that at the moment. You can also only need one terminal open because you can drop into this shell mode. So say you wanted to like run some other command. If you're used to Unix commands, like to look at what files are in this directory, you might type ls. So you can see I'm here in my home directory with a whole bunch of things, and you can copy files around, run a whole bunch of Unix programs if you're working with some of those, all from inside of Julia, just backspace back to go back to the Julia environment. Cool. And then the last kind of major mode that's really helpful for people learning Julia and makes it a really nice interactive environment is the help mode. So if you go ahead and press the question mark like that, but without, of course, the quote in front of it, it moves you into this help mode, you can see. And now I could type something here like, I don't know, help me with this square root function. So you can see, et voila, it gives you a bunch of examples of how to use square root, tells you when it'll throw some errors if you're using negative arguments, gives some examples of things here. So here's some example code that you can run. You can see it works on things like imaginary numbers. It works on matrices, gives you all of that different information, and that's built in right into this Julia REPL, so you can access it quite quickly, and that works for anything. It also even works for if you do the LaTeX symbol for square root, just that little square root symbol there. That'll give that same help list, which is very exciting. Search, there we are. Can be typed by doing square root tab. There you are. So that's the Julia REPL. That's something you might end up working with if you install Julia on your own computer, but in our particular case, we're using something a bit different called Pluto.jl. JL is the file extension for Julia, so lots of these Julia packages will have that on the end of them. So this is a bit like a Jupyter Notebook, as I'm sure some of you familiar with Jupyter Notebook can tell, where you've got your code cells, code that can be run next to written words. But it's different in a few ways, like, for example, it's reactive. So instead of having to rerun all the cells, which you might have to do if you're in something like Jupyter Notebook, say here we've got these equations down here, and if you change x to, say, 4, and then you save that, that automatically reruns these next two cells as soon as this one is saved. So it can tell which bits of other code depend on what code, and it reruns those when you're changing something that they depend on, which is quite cool. So we'll go back to 3. Nice. So if you want to play with it yourself as well, I might as well open this up and send a cute little link to it, actually. So copy link. You don't have to follow along for this session. In fact, you might struggle a little bit once we get to the later parts where I have data downloaded on my computer that you might not necessarily have. But if you do want to follow along, or play with Julia in general, without having to install it, there's a cute little website where you can pull up a Pluto notebook a bit like this and test it out yourself. There's also some nice examples that Pluto has built in that show off how to do some much more advanced stuff than I'm doing in this notebook. You can make like interactive things, which is really cool. So, all right, time for our whirlwind tour of some actual Julia code. We'll start with talking about how it makes mathematical notation real nice. So one thing you've already kind of seen is how you can input those special symbols like pi or square root. Lots of these symbols are already bound to their real mathematical meanings. So as you can see here, this is just finding the radius of a circle with the area of 20. So there's our equation, which is written much like you'd see it in maths, with the square root of the area divided by pi. And you can just put in the pi symbols and the square root symbol, and it'll calculate it just from that. And you can see, obviously, if I change the area to make it bigger, the radius will go up as well. So you can write things quite naturally with these Unicode characters, which is a pretty unique feature, I think, of Julia. You also have these literal coefficients, which just means, again, like you'd write in maths, where you might write 3x, and you leave out that implied multiplication. You can do that in Julia as well. So instead of having to write 2 times with, like, you know, your times symbol, and then 3 times, which makes that whole thing a little bit challenging to look at, but it means the same. You can simplify that down into the mathematical notation with just, you know, 2 and 3x. So that's another way it makes doing maths and scientific computing easy. That obviously works for exponential equations. This is 2 to the power of 2x, which is actually even more clever there, I think, because the 2x is a higher precedence in the order of operations than an actual multiplication symbol. So you see here, it's reading this as 2 to the power of 2 times x, so that's going to be 4 times 3. And you'd have to put, you know, brackets around it if you wanted to compute what you actually want it to. But that obviously isn't nearly as clean as just writing 2x. So there you are, nice and optimized for some clean-looking code. Further along, it's, you know, support for nice mathematical things, as you have imaginary and rational numbers built in. So IM is the imaginary number I in maths, or J if you're used to it in engineering or MATLAB. They've made it IM so it doesn't clash with variable names that want to be I or J. So as the square root of -1, if you square the square root of -1, it just becomes -1, and you can see that with no imaginary component anymore. Here you can see you're multiplying 2 into these brackets. Again, you don't need to put that explicit multiplication there, and that's being multiplying both the imaginary and the real component. You also have things like rational numbers, so you can write 6/9, and you can put these double slashes to separate them, and it simplifies it down to the simplest possible fractions. That's the same as 2/3. Here, you know, it makes it -1/2. If the sign is on the denominator, it makes the denominator always positive and the numerator negative, so it turns this whole thing into -1/3. Obviously, just simplifying fractions isn't the most useful thing. You can actually operate with them. So you can do something like 3/4 times 5/6, which if you multiplied through by hand, you'd get 15/24, and then it goes and it does the simplification, divides the top and bottom by 3, and you get 5/8. Nice thing about this as well, if you're familiar with some of the problems that computers have with floating point numbers, which are those numbers with decimal points after them, they can lose some precision, so they can lose some accuracy. In fact, I have a really good example of this down here, where I've had to put in this round operation. If I'm not rounding those numbers there, you can see this is basically 1. It's 0.999999, a bunch of 9s and then eventually an 8. And this cute one over here is -2 to the power of, or times 10 to the power of -17, so incredibly small number. Those aren't actually mathematically meaningful. Those are just errors that come from the computation. But with things that you can represent as rational numbers, these won't have those same losses in precision, which is really nice. Of course, not all numbers are rational. Pi, for example, is of course irrational, so you can't, represent pi as one of these rational numbers. But for things that you can represent as rationals, it's much cleaner. Well, you can avoid some of those floating point errors by doing so. Onwards, I guess you have matrices. Matrices are a pretty big deal in lots of modeling. In fact, in the last one of these Coding with Biology sessions, we were talked through how to do some systems biology using stoichiometric matrices. So Julia has nice support for matrix literals. So you can see here we're writing this 2x2 matrix, and you just put a semicolon to separate a row from the next row, spaces to separate columns. You can do matrix operations, so say here multiplying this original matrix by 1 over the square root of 2, you can see that multiplies that whole thing into that there. You can also do matrix multiplication, which is a bit of a complex operation sometimes, and it depends on the order of things, but here, for example, is this matrix, which is 1 and 1 scaled by 1 over the square root of 2, and it's this vertical thing here. This little apostrophe actually transposes the matrix, so you can see that's caused an error down there for its wrong dimension. So to make this rows into columns, put in that transposes it, now it's a vertical. Yeah, and then you can do some operations like here, multiplying those two matrices together to get a matrix output. Another important thing is this use of the dot for like broadcasting. That means apply this function to all of the elements of something. So if you imagine trying to round a matrix, that doesn't make too much sense. How would you round a matrix? It's got a whole bunch of numbers in it. But if you wanted to round every element of a matrix, that makes sense. So you can just add a dot after any function, and instead of applying it to that whole thing, it'll apply it to individually to every one of its members. So this rounds both of those numbers individually inside of the thing. This also works with, like the square root. How would you get a square root of all of the numbers from 1 to 4? If it's a list, it doesn't really make sense. But if you apply it to one item at a time, you can see that makes a bit more sense, maybe. Cool. So we might see those things pop up a bit later. Last thing to talk about then, really, before jumping into the actual growth curve analysis, is just all of the scientific packages that are available for Julia. In fact, I might pull up their website real quick, just because they have a nice example of a whole bunch of things. Et voila, Julia programming language. Yes, goodness, that is quite large, isn't it? So they have an example of the ecosystem here, a whole bunch of plotting packages, certainly ones, enough to keep you busy with choice. That's talking about some of the general purpose stuff, but we might be interested in data science stuff, so, for loading from CSV files or working with data frames, which you'll be familiar with if you've done much data processing in Python. They're a bit like spreadsheets, but in code. Machine learning stuff, other scientific domains, so it's got great differential equation solvers and optimization tools for doing fast Fourier transforms, quantum computing, all sorts of stuff, very easy to get a hang of. So even though it's not quite as mature as Python, there's a real focus on developing quite quickly all of these scientific computing tools. And of course, there's parallel computing. So here they have the example of them using a supercomputer and running one Julia program on, 650,000 processor cores, which is quite impressive. So that's just an example of some of the other things that are out there to find. Cool. All right, I think we ought to kick on with actually doing our growth curve analysis. So this part I'll just kind of go through and I'll write the code and explain it as I'm going along. But just so people have a handle on what we're starting with, here's our growth curve data that we're going to be processing. We're going to see how this ends up looking when it loads in this cute little spreadsheet, because I don't actually know how big it'll be, how easy it'll be to see on the screen. It'll certainly take its time. Okay, cool. So, yes, I did that. This lovely little spreadsheet here is the result of one of our longer running experiments in the lab, where we're trying to optimize growth media for this particular microbe called Vibrio nitrogens. Here we're using we're testing 25 different media recipes. So each one of these numbers is a different media, so a different, food for these microbes. And then down the y-axis, you can see here's the amount of time that those experiments ran for. Now, there's some things that make processing this data a bit challenging, which you can probably see right off the bat. For example, some days we got kicked out of the lab early. Whoops. Other days, we got to run these experiments for much longer, and so there's more data in those growth curves. These are ones that ran out to 4 hours and 40 minutes. But you can see that, there might be something we have to do to, deal with the difference in size of each one of these data sets. But that's what we're going to be loading in. So let's take a look at how we can load that into Julia and how we can work with it from there. Let's bounce back over to Julia, or the notebook even. Cool, and then I'll pull up my cheat sheet on the left where I prepared all this code earlier, and we'll crack on with it. So, first thing that we'll want to do is load in some packages for working with all of our Julia data. We'll want to start with some things for loading CSV. So there's a package called CSV, and you can just kind of list, after using all of these different libraries that you want to pull in. We'll be working some with dates, because we need to calculate the amount of minutes that are between things like, 0000 and 0440. So these times, these 4 hours, 40 minutes, or time 0. How do you actually convert that into minutes, or some other, continuous number? So dates will help us do that. Data frames, of course, are the structures that we'll be loading this spreadsheet style data into. Gadfly is a plotting library that we'll be working with a bit. GLM is for generalized linear models. It's a very fancy, term for that's our regression library that we'll be using to do like lines of best fit a bit later. And then finally, we'll just pull in the built-in Julia statistics library. So there we are. Go ahead and run that. And you can see it goes ahead and it gives you little check marks if things are installed in the notebook. Or you saw maybe briefly there some swirls that meant it was loading or installing those packages. And of course, this little stripy line down the left here means it's currently loading and running that cell. So you can see, like I mentioned earlier, there's a bit of a tens of seconds of delay the first time you might run some code before you can get a result out, because it's doing all that compilation before you use it, so it's quick when you do run it. But from that, we can move on from loading our packages into actually loading this CSV into a data frame. To do that, we're going to want to first create a little a name for our, or give the name of our, are we fussed with that? No. So we'll create a new variable, df, for our data frame. We'll say that it is a data frame. This object, or this notation is a bit similar to like Python, if you imagine like creating a new object or something. So for our data frame, we're going to create that data frame from some CSV, and you take the CSV file, or the CSV library. .file is for loading a file, and we want to load the file that is called growth curve data.csv. So you can see that looks quite similar maybe to how the Python code would look. If we go ahead and run that code, we can see, after it takes a bit of time for its first run there, what our CSV looks like. Cool, so we'll give that a moment. Yeah, thanks, Julia, very quick. Okay, while that's running there, being a bit ominous, we can also think about our next problem, which is all of our data here is in something called wide format. So you have these rows or columns, and if you imagine when you made a 26th media, you'd be adding a new column here on the farthest right. That's actually a bit difficult to process sometimes, because spreadsheets, lots of programs are optimized to process them as there's kind of like the type of data is the column, and then it just kind of runs down. So maybe you could imagine a thing where you have 3 columns. You have the time, then you have the type of media, which is one of these numbers, 1 through 25, and then you have the OD, which is how much it's grown. And so you could tell from one row, there's only 3 columns, what the OD is, which media is being tested, and what time it's at. That's a lot easier to process, which we'll see in a minute. But obviously, as you can tell now, here it's loaded it in that same wide format, where things go across to the side. And we can also see where our missing data is, where there might be some data that goes all the way out to that time point, but others that do not. So there's a few things we need to address there. The first of which is we'll do this conversion to the long format. So I'll go ahead and take this data frame up there. I'll call this LDF for the long data frame. And you can use the function called stack. We'll give it this data frame, and I'll talk about what stack does in just a moment. We'll say to take columns 2 through 26, which is starting with this second column here right after time and going all the way out to 26, because we have 25 total medias. So if you're counting time as a column, that's column 26 out there. And then you have to tell it, let's see, what's a good idea to start with? Yeah, so then you can add in some optional arguments. One of them being variable name, and we'll go ahead and say that's replicate. So replicate is something you don't see anywhere yet, but I'm trying to think if there's a nice way to do this. I might do this in the other order so you can see it a bit more clearly. So we'll start instead with value name. Here is OD, and we'll go ahead and run that code. Hopefully that won't take too terribly long to load. Yeah, there we are. Cool. So what this has done here is it's taken all of those columns from 2 to 26, and it's taken the values in those columns, all of these, numbers here, and including the missing bits. It's taken all those and put those in a column called OD. You can see also it's created this thing called variable here, and that is storing which column things originally came from. So you can see some came down there from 25. If you press more, you can see all the ones in the middle. So now you can see this is in that long format I talked about earlier, where there's the time, there's the replicate, or the type of media, and then there's the OD in its third column. And all of that now is in one long data frame. What I was doing a moment ago when I was adding the whole variable name replicate is that's literally just taking this thing here that's called variable and renaming it to replicate. So I do that, and now it says replicate 1 or replicate 25 or whatever. Cool. So now we have our data in long format, but there's a bit of a problem, of course. These rows here that have missing data aren't going to do anything good for us at all, essentially. We'll just have to work around them the whole rest of the time and make it so all of our code, like that's plotting things, checks for missing values, and that would be a bit of a faff. So for us, because they contain no real data, we can just drop them. So there's a function in Julia called drop missing, and you can just put, all of this data here, feed that into the drop missing function and run that, and now, et voila, all those missing values are themselves missing. One nice thing as well that Julia lets you do, this is just a different way of writing the same code, is you can imagine if you continue nesting functions inside of each other like this with all these brackets, it might get a bit visually confusing. It sometimes makes sense to think of things as a process. So say you're starting with stacking the values, and then after that you're going to drop the missing ones. To write that in Julia a bit more clearly, you can use this little chaining operator. So that vertical line, the pipe, and then I guess that's the greater than sign. You use that kind of points to your next operation, which is this drop missing. You go ahead and run that, and now you can see it does the exact same thing. The code is done, it's run, it's the same value. If we get rid of it, obviously, it will probably give an error yet because there's that thing there. But you see, there's the missing ones, add it, and the missing ones are gone. Cool. So the thing that I said I was going to show earlier about explaining the stack function is another nice thing about Pluto, this notebook environment, is it has live documentation. So if we pop open this, it says blah blah blah, welcome to live docs, and they'll give you some help with your code as you click on it. So drop missing is the last thing I typed, so that's why you can see this code here. Return a data frame excluding rows with missing values. Well, that is indeed what it's done. How nice. But if I click on something like stack over here, now we get the documentation for stack. So this is stack a data frame, i.e. convert it from wide to long format. And then you can see there's even, here are the options for variable name and for value name, and say which the measurement variables are. So that's like the columns to pick. And you get a whole bunch of information here talking about what all those things do, and some examples written in Julia code, nicely formatted. So you can imagine if, for example, you were to look at this code later on and you forget what stack does, you can just pop open this little window, click on stack, and learn a whole bunch about it right here from inside of the notebook. I guess I'll keep that open as we go along, just because it might be helpful for people to see. Nice. Okay, so here we can see we've got our long format data, no more missing columns. That's nice. We've made some good progress. Now, what we might want to do is normalize all of these times and convert them down to minutes. So instead of having, these hours, minutes, second timers there, let's just convert them all to be a number, and that's the number of minutes since this first measurement. This one starts at time 0. That might not always be the case, but, we'll write the code to account for whatever that starting time might be. Cool. First thing to do is to get that starting time. So if you go ahead and do start, and we can create a new variable for that starting time. Here's the data frame. You can select the first row by using 1. That's actually an important difference between Julia and Python. I think MATLAB is the same way, though. Python starts a list at 0. Julia starts a list at 1. It's always a bit of a controversial difference, but just something to be aware of. So 1 here does actually mean the first row, not the second, like it would in Python. So we can put in 1, and we'll say I want the data from the time column. So go ahead and do that, and voila, there's our start, our starting time being 0. That makes sense. That's what we see there. Cool. Now what we can do is we can actually create a new data frame. I'll call this one PDF. To be entirely honest, I forget what the P there means. Processed data frame, probably. That's literally a random name. That could be anything you want. The reason it's PDF is because that's what I have in my example code on my other screen, which I wrote a while ago. So I think that's processed data frame. Just another version of this same data frame, but we're going to do some transformations on it. So we can pop in transform here. Transform is going to take a data frame, and then what it's going to do is take some operation for how to change it. So what we want to transform in this data frame is this whole time column. We want to take these times and turn them into minutes. And so to do that, we can say, all right, I want you to give me all the values in the time column. So this is running a transformation on time. And then for every row, so you do a by row. Some of this is a bit like tricky bits of Julia. Obviously, I can only really give a cursory glance at some of this stuff and not a terribly in-depth exploration of things like by row or, all the things that transform can do. But obviously, if you're more curious later on, I'll be sending out this notebook, and you can play with the help file here and, Google about and check out some of the documentation for yourself as well. But for every row, we're going to take some variable time, which is what it's going to be the input, and we want to calculate the difference between that time and the start time. So one way we can do this, I think if we just do time minus start, that might behave to begin with. But after we do that transformation, you can put this into a different column, but we want to put it back into the same column. So we can do that. So what this means is take data from this time column for every row, find the difference between that time and the starting time, and then put it back in that same time column. Yes, of course. Something about Pluto that's quite unique is that it doesn't quite like having 2 lines of code or multiple expressions in one block. So it'll either tell you to split it into different blocks or wrap it in begin and end. Here we'll just split the 2 up. So I'll take and copy that code and add it down here. Sick. Okay, go ahead and run that, and run that, which is now running. Cool. Wow, that's interesting looking, isn't it? Oh, of course. And now, instead of DF, we want to use LDF, which is our long data frame. So that's me being silly. That's why it's gone back to being wide. Okay, there we are. Sick. So there you are. You can now see some strange things going on here. We're measuring in nanoseconds, and it seems to be a little bit confusing what exactly is going on. But those are indeed the differences in time, just measured in nanoseconds. But we can reformat that by going ahead and doing, for this date that's returned, saying give us the minute. So this is going to convert those nanoseconds to minutes. Et voila. Now you get 0 minutes, 20 minutes, 40 minutes, blah, blah, blah. Obviously now it also says minutes after it. It's not quite a real number. If you hover over up here, you can see what types all the values are. This is a special minute type. It's not just a number. We do want just a number, so the last thing to do that is you can do dates value, and that'll extract the actual value from the minutes thing and give you the number back instead. So there we are. Now we have just our numbers. It's a 64-bit integer, so that is just a plain number that we can work with like it is one. Cool. Okay, now we have all of our data ready to actually do some plotting with. So, as a bit of background, OD, which is what we're measuring here, that's optical density, is proportional to cell count within a decently diluted range. The more light that's scattered, the higher the OD, and that's the amount of light that's scattered is proportional to the number of cells in the liquid that are scattering the light. So on a linear scale, this growth curve is exponential, because you imagine, you know how microbes grow, where they double, and then they double, and then they double again. It's exponential growth. But we can make this linear by applying a logarithmic transformation. So that's kind of like going to be our process we go through here. Cool. So let's go ahead and give plotting a shot. So we're going to try and plot this processed data frame. On the x-axis, we're going to want that time value. And on the y-axis, we're going to want the OD value. And then the color of these lines, so we can plot all of these replicates on one graph, is going to be the replicate. So I'll go ahead and do that. That should give us a basic plot. Hopefully it won't take too terribly long to load for the first time. But we'll give it a go. While that's going on, we can start thinking about other things to add to the graph. Like, for example, you might want to add a label on the x and y axis. Just to show that off, we can do some adding of guides. So you can add x label, is how you'll add something to the x-axis. So here I might want to say, well, on the x-axis it's minutes, because that's our time that we converted into minutes. And then maybe on the y-axis it'll be something like OD600, so guide y label OD, and then 600 is the wavelength we did that. I think I should be able to do underscore 600 and then enter. Yeah, and you see that makes that really small 600. That's more of that LaTeX code coming in action, or coming in useful, I guess. This graph is taking, Christ, took its time there. I think that's because I'm also streaming this out and also recording it. My computer's a little hard pressed at the immediate moment, so that's longer than even it should normally take. But there you are, you can see that. Time and OD. If I rerun it now with those guides put in, oops, what have I done? Forgot a comma there. If I put it in with those guides in, now you can see OD 600 in minutes. And you can give the thing a title as well. So, you know, guide. I'll make this look nice, put it in the same place with a comma there. Guide, and then do title, and put, you know, whatever there. Cool. And you can see up pops a title. So that's how you can do that. I'll pop in the title that I have for my other graph. You can use, like, for italics, you can use the HTML thing for italics. So that'll italicize the name of this species name. So you can see there you are. Pretty cute. Nice. Okay. So this looks overall pretty reasonable. You can see here there's a bunch of different replicates. You can turn on and off different ones to say that teal one looks like that might be 24. Yeah, so you can toggle on and off particular lines and see where all those dots are, and you can kind of see this exponential growth process with them growing at very different rates, these different medias. To get a bit of a closer idea or closer look at what's going on here, we can plot things on a log scale. To do that, we can take this exact same code that we've just made for plotting it on a non-log scale and pop it into this next cell and go ahead and do something like scale, and you can say y log, x log, and like log. Like that is normally the natural log. I want to do log base 2 because we're talking about doublings of bacteria here, so log 2 is a quite natural thing to work in. So if I do scale y log 2, go ahead and run that, et voila. So now you can see our axis labels over here have changed for the y-axis. They're now, the logarithmic representation. And here you can see parts that were before exponential, like this region here, have now become linear, which is exactly what we were looking for to match a nice line of best fit to this in a moment. So here's our log transformation of things. It's kind of made these curves a bit easier to interpret. And this is the sort of thing that you'd see in most growth curves. They're log transformed when you look them up on the internet, just because they're much easier to understand, where you have this exponential growth phase, this linear upwards bit, then a stationary, and then some death phase, which might be a linear down one. Cool. Okay. Now what we might want to do is go ahead and look at one of these growth curves in particular. So we want to split them up by replicates, or these medias. There's a nice operation for doing this. This is one that's in the data frames library. So we'll create a grouped data frame, this GDF thing. Again, the names can be whatever you want. They're pretty arbitrary. I'll do group by, and then you go ahead and pop in something like our process data frame, and we want to group them by replicate. So if I run that, just checking that all is going well. Yep, people are still kicking around. Cool, so if I group them by replicate, you can now see there's a bunch of different data frames here, a whole list of them. There's 25 groups, but every one of these groups is a miniature data frame that just has either just replicate 1 or just 25 or something like that. Cool, we'll let someone in. There we are. Nice. Yeah, so here are our group data frames. So now we can look at individual growth curves instead of all 25 of them at once. And I think, yeah, we started with all of our replicates. They're grouped up anyways. But the nice thing about this group by operation as well is that this group by operation works even if things aren't all next to each other in the list. So you can imagine if we want to group them by time, so we look at all 25 of the medias at time 0. That's a bit hard to do here visually because there's a bunch of things between every one of them. But this group by function works. You just change replicate into time and run that. Now we should have a bunch of different groups. And so now you can see at time 280, only 3 medias made it out to that time, 8, 10, and 22. That's what their growth was at that point in time. And now you can see there's 15 groups, so 15 time points instead of 25 medias. Here at time 0, you have all 25 of the medias, for example. So you can kind of group things differently that way, which makes them easy to look at things that you're interested in. So because we're interested in the difference between replicates, we just want to get groups of each replicate, so individual growth curves out of this list of 25 of them. Sick. Okay. So let's pick a replicate to zero in on then. This is what I mentioned earlier, where you can put things in one block with a begin and an end. We'll have several lines of code in here. I'll be having to think about if that makes much sense. I think that's reasonable enough. Yeah, so here we can say, just create a new variable called curve. I want to look at, say, curve 25. So now what we can do is take our same plotting code from earlier. I'll take this log transformed one here. Yoink, and pop that in here. But what we want to do now, which is different from before, is instead of plotting the whole data frame, which I can show again, there's the whole data frame with all 25 of them on. I want to go to this group data frame, and I want to get data frame 25. which will be this last one here. This is replicate 25, so we're just going to plot this one growth curve. Once you group them in that GDF, you just say which number you want in these little brackets here, and you can see it. Dun, 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 et voila, there's our nice little curve for 25. Obviously, though, I want to make this 25 something we can change easily, which is why I created that curve variable, just so now we can go ahead and say, well, okay, if I want to look at curve 1, I change curve to 1, go ahead and run it. There's curve 1. Curve 16 would be that one, or curve, 20 is that one. 20 was a bad media, that didn't go anywhere. Sick. So that's how we can focus on a single data frame. Let me see if there's a good example of one here. So one that has a nice looking curve looks like this light teal, which I think is 15. That's not 15. Maybe it's 20. Maybe it's 23. None of those. Is it 1? 9. 9, yeah, okay. So that top curve there is 9. That has this nice looking shape. So I'll pull in 9 so we can look at that one a bit closer. Dun, dun, dun. Sick. Okay, nice. So this looks like your typical growth curve. We've got a bit of a lag phase at the beginning, maybe. Quite small. This exponential growth phase where it's a bit linear, and then you tail off and you hit a stationary phase where your growth has been maxed out. What we want to do is fit a line to this log phase to get an exact idea of how quickly things are growing. So what we want to do is trim this data a bit. To do that, we can go ahead, pop down here, and look at this data in the log phase. We'll create a log data frame, and that will filter from our grouped data frame. So in the filter, we want to take that time column, and for every time t, we want to check if it is bigger than some arbitrary number. So in my head, I might want to select, for example, here, which would be 20 minutes, probably, because we did our readings every 20 minutes. So we'll go from 20 minutes up to this point here at 100 minutes. That seems like a pretty linear region to me. So we can go 20 to 100 minutes. So 20 greater than or equal to the time, which is greater than or equal to 100 minutes. So that's another nice thing that I think you're able to do in Python, maybe not in some other programming languages, but you can write compound expressions like this with these less thans and greater thans. You don't need to do something silly like you might need to in other languages where you put and t is less than that, where you repeat the t. You can just, again, write it like you would in mathematics. T is greater than or equal to 20 and less than or equal to 100. Cool, so we're going to filter all of the times that meet that criteria, and we're going to filter those from our grouped data frame and the curve in particular that we're looking at. Sick, so go ahead and run that. Et voila, now we have times from 20 to 100. There's our new data frame. That should be just this linear region here. Of course, should be is a bit fluffy sounding, so we'll plot that in just a moment. But before we do, you'll notice this OD is back to being not log transformed. When you put scale log y here, that's a purely visual difference. It doesn't actually change your data. To change your data, you want to actually run the log transform. To transform your data, you can use the transform operation. Julia has a bit of a convention. You might be wondering what that exclamation point is all about. In Julia, if a function does not have that exclamation point, like filter, you can trust that filter is not going to modify any of the data you pass to it. So we've given it our grouped data frame, and we don't actually know, maybe without checking the documentation, whether or not filter will take values out of the GDF, or if it will delete anything there or rearrange anything, or if it'll just return a new copy. Of course, if we look at the documentation, we can say it returns a copy, but we could also know that because it does not have that exclamation point, meaning it's not allowed to modify anything that you pass it. Transform, on the other hand, comes in a, well, exclamation point and a non-exclamation point version. But with the exclamation point, this will be modifying what we give it. So we'll give it our log df, and want to actually change this data. We want to look through that OD column. And for every one of the ODs, again, we'll do that by row thing that we saw earlier. So for every row of the OD, we want to do a log base 2 transform. And then we want to put that back into the OD column. And we can run that. Sick. So now you can see there's our log base 2 transformation. of the OD. Everything that's, below 1 ends up being negative. Things that are above 1 end up being positive, just like you'd expect from a log transform. Just to explain this syntax a little bit, I guess. This is obviously the input column, but this is the output column. And these don't have to be the same name. So if you want, you could do something like log OD. And now you can see, yes, okay, I've been a bit silly here. This is why people often try and avoid using these exclamation point functions sometimes. They're convenient, but at the price of their convenience is they do change your original data. So what's happened here is we've changed log_df so that there are negative numbers now, because we've done the log base 2 transform. And now then we've tried to take the logarithm of those negative numbers. We tried to do the logarithm twice, and that's thrown a domain error. To sort that out, we can just rerun this code up here. I think should be all right. Yeah, there you are. So now here you can see what I was intending to do, which is create this second column with the log OD next to the real OD. We, of course, want to go back to this OD. We'll save that. It'll throw us a domain error. Will it? No, but it won't get rid of that last column again. So because we added the transform the last time, the exclamation point does bring with it a lot of issues. So maybe this is a good demonstration. Because if we want to get back to the world where it didn't exist, you have to rerun the last one and then run this again, and that modifies it to be the log OD without the other column. Lots of stuff going on, so I guess the idea is, the takeaway here is be wary of things that transform stuff with, that actually mutate your values with an exclamation point. The other way to write this, of course, would be to do transform and then give it another new name, so like log df2 or something. And now you can see, yep, okay, we get a domain error again because we modified the last thing. Cool. So now you can see this is log df2, it's a new variable, but now we could do things like add log OD and run it, or change it back and it'll disappear again. So you can see it now no longer has those problems that the exclamation point did, but the exclamation point just saves us from having to create a new variable to copy it into. So there's that to be aware of. Two ways of writing the same thing. Cool. Okay, we're nearly there now to the end. Sorry, this is run on a little bit, but we're gonna actually plot. Will we plot it yet? Nah. We'll start with doing a regression of this data, because this should be our linear region here, and then we'll plot it all at once with the line of best fit to take a nice look at it. So let's do ordinary least squares regression. So to do that, we'll create a new variable to store the result of our regression, or line of best fit. We'll use a linear model, and then we'll give it a formula. So the formula that we'll be using, these you'll recognize from R. It's the exact same syntax, I believe. We want the y-axis, or the y variable, to be OD, and we want that to be proportional to the time. And then what we'll have as a result of this is this model will fit to our data that we give it, and find the gradient, the slope of that line, as well as its intercept. Note, of course, you don't have to specify the intercept explicitly in this little equation. Of course, then we need to give it the data that we're training it on, which in this case is log df, and go ahead and run that. So it'll think for a moment or two, because this is the first time we're using that regression library, so it has to do all that code compilation. It's that latency I was talking about earlier, which is always a bit of a killer, especially when your computer is, streaming out to a webinar of people. Cool, but while that's loading, oh, well, didn't even have the time. Cool. So here's the result. It's a regression model. You can see the intercept is something like -5, and the coefficient for time, so, the thing that goes in front of this time, the gradient, the slope, if this is the x and this is the y, is 0.05. And we'll see that's an important number for us in just a little bit. But you also get some nice statistics like the standard error, some t statistics, your confidence intervals for the, upper and lower 95% confidence interval. You get all those nice statistics there. Sick. So now what we want to actually do is use that model to predict if things fit this linear model perfectly, what all of their log ODs would be. So we'll add a cute new column to our log data frame. So here's our log data frame from earlier. Exclamation point means like apply this to all of this dimension in this context. So remember earlier where we had 1 here representing a row. So like if I do log df1, oh, okay, so it doesn't even like that particularly. So if I did that and then also said the time, so this will get the first row time for me. Now, of course, our time starts at 20 because we filtered this data frame down. We've restricted the time. We've zeroed in on a window. But if you go ahead and select with the exclamation point, that'll pick everything from that time column. So now you can see we had a list of the 20, the 40, the 60, the 80. So you can think of this as like apply to all of the things in this dimension, and this is the row dimension, this is the column. What we want to do, though, is create a new column called model, and we want to predict that column using our least squares regression. So if we go ahead and do that, we can see, et voila, there are our nice new values. These are pretty close, as you can see, to our real OD values. That is the point of the regression, is to try and match this data quite closely. But it would be easier to see, of course, if we plotted it out. So I'm going to go ahead and grab some plotting code. In fact, I'll grab it from our last bit of plotting code that we've done, which is up here. Yoink. Something that is different about plotting this time. There's actually a few things, of course, that'll be different. Spacing's a bit quirky. Cool. We want to plot our log data frame now. Same as before for the x, y, and the replicates. But you see we're going to get a bit of an error here. This is our familiar domain error, which is what happens when we try and do the logarithm of a negative number. Where that's come from is we still have this scale log y2 here. That worked when our data wasn't originally log transformed, but now, since our input is data that's already been log transformed, if we try and do that twice, we'll get an error. So we will have to remove that second log transformation. But you can see it still is this nice linear pattern because the actual data has been log transformed. Cool, and then what we want to do, of course, is add in our line of best fit. You can do that just by adding a new layer in the plot. So you can say layer, and this new layer is going to be an x, that is time, like before, a y, that is now the model. So that's our new column that we've just added here with the predicted values from that linear model. And we're going to say that's going to have the geometry of a line. Go ahead and run that. And it's going to cry because I didn't add a comma here. It's going to take a second to load for the first time. Sick. Voila. So now you can see there's that nice line. Of course, the problem here is that our dots have disappeared originally. That's because we've not given them an explicit geometry. If you don't give something an explicit geometry anywhere, it'll fall back to doing those dots, the points, the scatter plot like we saw earlier. But now that we put in a line, it's stopped making that assumption for the rest of our data. But if we want to tell it explicitly, make sure you also put in those points. You do geom point. And that'll toss back in our actual data points. So there you are. You can see there are the data points, and they all fit very tightly to that predicted line there, which is quite nice. Final thing to do then, as a wrap-up, is to predict the doubling time from our model. We've got this nice fundamental equation here, which is that the number of cells is equal to the initial number of cells times 2 to the power of, and then t over g. T, of course, is the amount of time that's passed, and g is the generation or the doubling time. How this equation works intuitively, you can imagine if you have one cell to begin with, so we'll make n0 1, and after one doubling time, you should have 2 cells. So if you want 2 cells here, you'll want to do 1 times 2, which means 2 has to be taken to the power of 1. And of course 2 will be to the power of 1 if you have your 20 minutes, and your doubling time is also 20 minutes. You have 20 over 20. So you can imagine that working for that. Say 40 minutes have passed and you have a 20-minute doubling time, so you'd have 40 on the top here, divided by 20 would be 2. So you've undergone 2 doublings. So 2 to the power of 2 is 4, and now you'll have 4 cells instead of 1. So you can see that equation, it makes intuitive sense here. We can do some simple algebra rearrangements to get it looking a bit more like our model here, which is this linear model. Do log base 2 to both sides, because our y-axis, remember, is actually the... see, this is poorly labeled here even. That's actually the log of the OD, so I should make that, log base 2 of OD. Is it gonna like that? Yeah, it'll like that. There we are. There we are. That's a bit more accurate. Because, yeah, we've done this log transformation, we'll want to get the y side of our equation looking the same. So we do log transform on both sides. That gets rid of that 2, brings it down. We can ignore this constant starting term here. That's going to influence our intercept, but we don't actually care very much about the starting number of cells, only about this doubling rate. So then we just do a last bit of simple rearrangement. Go ahead and take that t off of the top. So our t is like our x value. That's our time. And then our thing here is the log OD. And then you can see that the coefficient, this gradient here, is 1 over g. So it's just the reciprocal of this coefficient for time is our doubling time. To make that all a bit less abstract, what we can do here is calculate our doubling time with this little equation. So if we're going to get a value that's 1 over g, if we do 1 divided by the value we get, we'll get back to g. So we'll do our growth rate is equal to 1 over, and then we need to get the coefficient from our linear model, our least squares regression there. We want the second coefficient, because the first coefficient is going to be that intercept. In fact, I can show off what they are real quickly. I'll just copy that there, put it here, print it. So there's our second coefficient. You can see that matches that one that was next to t. The first one, of course, being that negative 5.5 intercept. But we're interested in the one that's connected to t. So there's that 0.57. And here, for time, 0.57. Hype. Okay, so last thing then is, let's just take that growth rate, which we can calculate there, or that doubling time. So that's a doubling time of 17.5 minutes. And what we can do is just put it in a nice string. These notebooks allow you to put like markdown in, which is a nice like just formatting language, I guess. So here I'll say the doubling time was, and then we can put in values in the middle. We'll say it was approximately, and then to put in a value, you put a $sign in front of it. So we could say approximately g minutes. Go ahead and run that. So now you can say doubling time was approximately 17 point and then a million decimals minutes. That's a bit goofy looking. You can't say approximately and then give some number out, to the whatever that is, the billionth or further precision. So also, if you put in brackets here, you can write Julia code inside of this string. And we can say, okay, how about you round that number, my dear friend, to something. So there we are, that rounds it to the nearest minute. But I don't want that little precision. It'd still be nice to have some data there. And if you've worked a lot with statistics, you might know about significant figures. As opposed to just rounding to a certain number of decimal points, you can round to a certain number of statistical or significant digits. And Julia has support for that in its function. Here you just say sig digits, significant digits, and we can say we want 3 of them. So now you can see you get 17.5. If we said 4 significant digits, it'd go out 1 further. If we said 2, well, that isn't any decimal points at all. And that brings us back to 18. If we said 1, that might just make it 20. Yeah, it just makes it 20. Cool. So there we are. There's our final doubling time. And the nice thing about this notebook now is that we've written and done this. We calculated 17.5 minutes doubling time for curve 9. But say we take a look at another curve here. I don't know, maybe this green one, is that 8? Yeah, maybe 8 is interesting to us now. And 8 looks like it might be a little bit slower than 9, perhaps. So if we go ahead down here to where we've picked our data frame, or our curve 9, and we change that to 8 instead, and run that, we now see here's a slightly different curve. The linear region we could repick if we feel it's not linear enough, but we can just check our plot. That seems pretty linear still to me. But now, of course, it's rerun. It's done a different regression. We have a different coefficient here and a different doubling time. So this one is slower. This is 22.8 minutes. And so you can see, you can even automate this process of going through all the curves. The only tricky part is finding which bit is linear, because that does vary from curve to curve for these ones that grow maybe slower, have lag phases. But the takeaway is you can just now go ahead through your notebook, change this curve number, and then instantly get, popping out the other end, a growth rate. And if you're ever curious about how well that growth rate has been calculated, you can see visually how well the line of best fit works, and you have statistics on hand to back up your claims. So that's a cute little example of what we've been using Julia for on our team in terms of data analysis. There's plenty more to check out. I think I'll be sending this notebook to everyone who signed up on the Google form. If you'd like to be sent both the recording and this file, but you haven't yet signed up on that Google form, feel free to pop your email in here, the chat, and I will be sure to email it out to you afterwards. In terms of further things to explore, where have I put my friend? Here we are. I've got some more Julia notes I might also send out. If you're interested in like actually doing, or if you've got some more software development experience and you want to learn more about some of the unique features of Julia as a programming language, this is a great little example here that talks about multiple dispatch in Julia, which is a way of writing functions that can save you a lot of code. So like, I think there's an example of, here's like some Python code which they write, which is really quite long and has a load of if statements nested in it. But the code becomes much, much simpler once you convert it to some Julia. Down here, where you can just say if it's a knight fighting an archer, if it's an archer fighting a pikeman, etc., etc. So that talks a bit about that, and it also talks a tiny, tiny bit about metaprogramming, which is a quite fancy, high-level topic. But if you ever imagine you're writing a program, perhaps you're doing some data analysis, and there's just something that's really repetitive, and you find yourself copy-pasting it every time. Metaprogramming is kind of insane. This is writing code that writes more code for you. So that's really like the next level of things if you're looking at making some short little code or some nice reusable code. If you hate copying and pasting, you really won't ever have to in Julia, because you can always write code that automatically generates everything you're copy-pasting anyways. And that's a really cool feature that they borrowed from Lisp. Nice. Okay. I have talked to people for quite some time now. I guess I'll open up to any questions if people have them. Otherwise, it was lovely to have people along, and I will send off this recording and notebook to you all afterwards. And hope you have a lovely rest of your day. But with that being said, I will stick around for questions, so if there are any, feel free to ask those now. Otherwise, have a lovely day. Cool. Thank you for coming along. Any questions, feel free to either type or ask with microphone. Up to you. Cool. I'll write down email. It's been sent. Yeah, thank you for coming along. I'm glad it was a bit of a nice introduction. Cool. Yeah, sorry, it was probably a bit whirlwind tour as well. Nice. All right. That's a wrap. What a wild adventure that one was. Enjoy that one in post.